When it comes to chemistry, we often find ourselves in a situation where we need to identify some unknown compound, or we want to isolate one target product from a cocktail of other chemicals. Chromatography, specifically when it's attached to a mass spectrophotometer, is a fantastic all-in-one method to achieve one or both of these goals and comes in a variety of familiar flavors like liquid-solid, gas-liquid, or even liquid-liquid chromatography setups. Like many other scientific instruments, mass spec chromatography also seeks to answer the age-old question: how do we achieve good resolution? How do we make these peaks sharper but not see overlap, or how do we separate the peaks without them becoming mushy and broad? Thanks to a Dutch physicist by the name of Jan Josef van Deemter, we have a way to determine this using a little something called the Van Deemter equation. Naming originality aside, this model allows us to determine the effects that diffusivity and linear flow rate have on theoretical plate height, which has a massive influence on the resolution of the peaks in the mass spec. The smaller h's, the better the resolution. Simple, right? Yes and no. When you get rid of the polish and the shine, you get something more like this. I'm sure you're thinking to yourself, wow, that's kind of a lot. And you'd be right. For an in-depth knowledge and understanding of the entire equation, I'll have to defer you to your local instrumental chemist. For now, I'm going to be focusing on one term in particular, the mass transfer term. Let's clarify a couple things right out of the gate. First, mass transfer simply refers to the transfer of mass from one place to another. Big surprise, I know. For our purposes, that mass is going to be our analyte, and it'll be moving from the stationary into the mobile phase, or vice versa. Second, when we use a C to represent mass transfer, in reality we have a 2 for the price of 1 situation going on, since C encompasses both the peak broadening contribution from the mobile phase as well as the stationary phase. First, we'll take a look at the mobile phase contribution. This effect comes into play as a result of differences in the linear flow rate closer to and farther away from the stationary phase. So what does that mean? As the analyte diffuses out of the stationary phase, it is swept up by the mobile phase and, depending on the flow rate, will travel a certain distance down the column like so. This is kind of like a boat trying to travel directly across a river and getting pushed farther down. The catch is that the linear flow rate is slower closer to the stationary phase, and that produces a sort of stratification of the analyte that we end up seeing as peak broadening. You can see from how the term is constructed that the magnitude of CM's effects is related to not only how easily the analyte diffuses out of the mobile phase and the linear flow rate, but it also depends on the particle size in a packed column or the column's radius in an open tubular column. Next, we have the stationary phase contribution. Imagine this: a bunch of people waiting to run into a store because there's a big sale going on. Once the door slides open, people begin to head in, not in a huge group, but in a line because the door is only 1 to 2 people wide. Once a few people have finished shopping, they leave through an exit door that is not blocked by the people still trying to get in and take advantage of those sweet, sweet deals. The analyte particles in the column act in the same way. You can imagine this grouping of analyte in the mobile phase as the sliding door, and as it moves further down the column, it allows some of the analyte that was previously covered in the stationary phase to begin to diffuse out and join together with the clump of analyte that had previously kept it in solution. Then, the reverse process happens on the other side of the analyte band, where some of the analyte in the mobile phase will push into the stationary phase to maintain the dynamic partitioning equilibrium. Here, the extent to which broadening occurs will depend a lot on how well the particular analyte can diffuse out of the stationary phase. The longer it takes, the wider the section of analyte that will diffuse out, and the broader the peak will end up being. This will occur if the stationary phase is really thick and it just takes more time to travel up and out, or if the diffusion coefficient is really small, indicating that the analyte innately has a lot of difficulty diffusing out. While it's good to understand mass transfer in its entirety like this, it's not necessarily required in practice. So what are some big takeaways? 1. The C term that we see in the equation is the sum of both the mobile phase and the stationary phase contributions. 2. When it comes to C, there's a positive linear relationship between linear flow rate and H. That means when flow rate goes up, your resolution goes down. 3. Both C terms are inversely proportional to the diffusivity of the analyte in the particular phase. The worse its ability to diffuse, the worse your resolution is going to be, so take the time to consider what aspects of your column may be exacerbating these effects. By understanding the C term, we end up being just one step closer to optimization and the ultimate goal of nice sharp peaks.